In this video, we try to understand the basics of a recurrent neural network and how it can be used to predict the price of a stock. We will first have a look at how a recurrent neural network works, and then see how to validate the network. Finally, I will show some simple codes in R and Python so that you can try the examples shown in this video. Recurrent neural networks are used in, for example, speech recognition, time series predictions, and language processing. Suppose that we have the following time series data that might, for example, represent how the price of a stock has changed over the past 2 weeks. This is the weekdays, and this is the price over the 10 days. For example, the price was $9 the first day, $7 the next day, and $6 the third day, and so forth. By using a recurrent neural network, we can predict if the future price will go up or down. The first thing that we should do is to normalize this data, because training a neural network works best with normalized data. One way to normalize the data is to use the min-max normalization, where each variable is scaled so that it has a range between 0 and 1. The maximum value in our data is 12, whereas the minimum value is 6. If we now plug in the first value here and do the math, we see that the normalized value for the first day is 0.5. Let's put the normalized value here. Next, we plug in the value of the second day. If we round the normalized value to 2 decimal places, we see that the normalized value for the second day is 0.17. These are the normalized values for the other 8 days. Note that the smallest value is now 0, whereas the largest value in the dataset is now 1. Plotting the normalized data will not change the pattern of the time series. It will only constrain the values between 0 and 1. We can think of x as a vector that holds 10 values. I will now copy these values and place them here. Let's denote this row of numbers as vector y. If we place the 2 vectors here, we see that y is a vector that holds the same values as x, but values for 1 day forward in time. Since the 2 vectors need to have the same length for our example, we will delete the last value of vector x. We therefore delete this value. We will now give the network this data as input and train it so that it predicts the normalized price of the stock 1 day forward in time. A recurrent neural network consists of an input layer and a hidden layer which uses values based on previous time steps. This creates a loop or recurrence which allows the network to use its previous states to influence the current state. The network therefore includes some sort of memory of values from the previous time steps. Finally, there is an output layer that stores the predicted values generated by the network. The value of the hidden node is calculated like this, which is based on the value of the input node and the value of the previous hidden node. These are the weights that are multiplied by the input node and the previous hidden node. The values of these weights are optimized so that the network predicts as good as possible. This is a so-called bias weight that is also optimized. This symbol represents that we will use some sort of activation function. There are several different activation functions to choose between, but I will here only use the sigmoid function throughout this video. The sigmoid function is also called the logistic function. The sigmoid activation function looks like this, where E is the Euler's number, and Z is the value we get when we add the terms within the brackets. Suppose that the value within the brackets would be equal to -2. Then we plug in -2 in the activation function and do the math, which will give us the value of the hidden node. The output node is calculated like this, where this weight is multiplied with the value of the current hidden node. This is the bias weight associated with the output node. The sum of these two terms is then inserted in some activation function, for example the sigmoid activation function, in order to compute the value of the output node. Note that our simple neural network only includes 5 different weights. Even though we would include more time points in our dataset, we will still have just 5 different weights. In this simple example, we have only one layer of hidden nodes. Adding more hidden layers will result in more weights to tune on. More weights to tune on usually mean that the network learns better. Let's unroll this network to better see what's going on. This is the unrolled network for our example data. Since we have 9 time points that we like to plug in into the network, our simple network will have 9 input nodes and 1 hidden layer. We'll here use an equal number of output nodes as there are input nodes. When we have many input nodes and many output nodes, it is called a many-to-many network. One can also design a network with, for example, just one output node, where the network is now called a many-to-one. I will show how such a network works at the end of this video. Let's plug in the normalized values of the stock in the input nodes, like this. Then we place the values that we like to predict above the output nodes, so that we tell the network the true values of the normalized stock price one day forward in time. These are called our target values. We will now train this network, which means that the values of the 5 weights are optimized, so that the predicted values of the output nodes are as close as possible to the target values that we like the network to predict. Let's zoom in on this part to see how the calculations are done. The network starts to give these 5 weights some random values, and after a number of cycles or epochs, the optimal values of the weights might be equal to these values. I will later show how these values are generated. We'll first start to calculate the value of the first hidden node with the following formula, where we plug in the value of the weight, the value of the input node, and the value of the weight between the hidden nodes. This is the value of the previous hidden node. Since we now calculate the value of the first hidden node, we do not have any previous value. We therefore set h0 to 0. Finally, we plug in the value of the bias weight. If we add these terms, we will get the value of negative 4.14. If we plug in this value in the sigmoid activation function and do the math, we see that the value of the first hidden node should be equal to 0.016. Let's put this value up here. We will now calculate the value of the output node, where we plug in the weight, the value of the hidden node, and the bias weight. If we add these terms and plug in the sum in the sigmoid activation function, we'll get the value of about 0.023 for the output node. Let's paste this value in the table. This value is the predicted normalized price one day forward in time. We see that the predicted value is quite close to the target value, which is the true value one day forward in time. Next, we calculate the value of the second hidden node, where we use the same weights as before, the value of the second input node, and the value of the previous hidden node. If we add the terms and plug in the sum in the activation function, we'll get the value of about 0.21 for the second hidden node. Let's put that value here. To calculate the value of the second output node, we plug in the weights and the value of the second hidden node. If we do the math, we see that the value of the second output node is 0.07, which is very close to the target value. We then calculate the value of the third hidden node to 0.81 and the third output node to 0.67. If we do the same calculations for the other output nodes, we'll get the following values. We can now calculate the differences between the target values, the true values, and the predicted values from the network. One measure to see how well the network performs is to calculate the sum of the squared errors, where we sum the square differences between the target values and the predicted values by the network. For example, this is the difference between the first target value and the first predicted value. The function that computes the sum of the squared errors is usually called a loss function or an error function. Note that there are a range of different loss functions that you can try. Another type of loss function is the sum of the absolute differences, where we simply sum the absolute differences between the target values and the predicted values. I will now try to explain how the weights are optimized during the training process. If we use the following weights, we will get the following output values, which will result in an SSE value of 0.31. Let's create a plot that shows the relationship between the sum of the squared errors and the value of this weight. I will here only use just one weight, because it will simplify the illustrations. If the value of this weight is equal to 6.93, we will get the sum of squared errors of about 0.31. Suppose that we now change this weight to 5.5. If we now do the same calculations as before, the network will result in the following output values, which will result in a sum of squared errors of about 1.33. If we instead increase the value of the weight to 8.0, the network will result in the following output values, with a sum of squared errors of about 1.14. If we would repeat these calculations for many different values of the weight, we could draw a curve like this to see how the error function changes when you change the value of the weight. This function explains why the value of the weight is set to 6.93 during the training process, because that is the value that results in the lowest sum of squared errors. To find the optimal value of the weight that results in the lowest possible sum of squared errors, the network is usually initialized by some random values of the weights. Suppose that the random value of this weight happened to be 8.0. Based on this value, the output nodes are calculated, as well as the error function. Then we used an optimization method such as the gradient descent method, where we stepwise move along the direction of the steepest descent. Suppose that the value of the weight is updated to 7.5. Then we calculate the values of the output nodes based on this new value, and sum the squared errors. One such round of iteration where we update the values of the weights and the output nodes based on all data is called an epoch. If we continue to iterate like this, we will sooner or later reach the minimum value of the error function. Since the slope of the curve approaches 0, the steps will become smaller and smaller. This kind of iteration is done for all weights at the same time to find the optimal set of parameter values that minimizes the error function. If we instead would have calculated the sum of the absolute differences, the error function would be quite similar. Note that, since the network starts with random initial values of the weights, and is commonly based on the stochastic gradient descent method, you will usually end up with different values of the weights every time you train your network. If you like to understand the details of the stochastic gradient descent method, watch the following video. In that video, I also explain how to use a certain batch size. To obtain these values, I ran 10,000 epochs to get a nice fit to the training data. I could have stopped at 4,000 epochs because the error does not reduce much beyond 4,000. The problem with running many epochs is that it will be computationally expensive and will often result in overfitting. I will discuss overfitting in a few minutes. In our simple network, we used only one layer of hidden nodes. Using several hidden layers or units will usually result in a smaller error because the network becomes more flexible since it has more weights to tune on. If we increase the learning rate of the gradient descent method from 0.1 to 0.2, we will reduce the error faster. However, a too large learning rate may cause instability of the gradient descent method, which means that it will not converge. Now, let's use the network to see if we can predict if the price of the stock goes up or down the next day, which is the Monday the week after. To predict the future value, we'll use our trained neural network with the optimal values of the weights. Then we simply add a set of nodes to the right like this. To predict the normalized value of the stock, we use the value of the previous hidden node and our last known data point. If we do the same calculations as we did before with the same values of the weights, the output node to predict the future value is about 0.04. Note that I here include the value of the last hidden node, so that the next hidden node gets information from the previous hidden node. If we only give the network one value, it will not get any information about the previous node, but it will still use the optimal values of the weights. By using the network to predict 1 day forward in time, it will predict that the price will go down. By using the predicted value as input for the next day, we can even predict the value on Tuesday. The network will therefore predict that the price will go up. Note that we here predicted 2 days ahead, but since we do not have any true values to compare with, we have no idea how good these predictions are. Also, note that a recurrent neural network usually predicts quite bad for many days, and is therefore usually only used to predict 1 day forward in time. Before we use the network in real life, we must therefore perform some sort of validation to see if it actually works on future data. Validation means that we check how well the network actually predicts on unseen data. Remember that this was the data we used to train the network. To know how well it can predict future data, we need some sort of validation dataset. Suppose that we have access to another week of data. We could then train the network on the dataset of the first 2 weeks, and then see how well it can predict the validation dataset that is unseen by the network during the training process. This would correspond to how well the network would predict future data. Same as before, we normalize the data, where we use these values for our input nodes, and these values as our target values to train the network in order to find optimal weights for the network. After we have trained the network, we can use it to see how well it can predict these target values based on these input values. Suppose that these are the predicted values by the network. These values are the true observed values. If we calculate the difference between the target values in the training data and the predicted values, and compute, for example, the sum of the squared errors, we will get the value of about 0.31, which is the same value we calculated before. We then calculate the same thing for the validation dataset. To make a fair comparison between the two errors, we should calculate the mean squared error to compensate for the different numbers of data points in the two datasets. We see that the mean squared error is much smaller for the training data. This is expected since the network has seen this data during the training. Maybe it has trained too much. If we plot the observed normalized values versus the predicted values by the network, we see that the network predicts the training data quite well, but predicts really bad on the validation dataset. Remember that we previously discussed how the error kept reducing during the training. The network therefore becomes better and better to reduce the difference between the target values in the training data and the predicted values. However, that is usually not the case with the validation data, because the network has not seen this data. Running too many epochs will usually lead to overfitting, where the network predicts the training data very well but performs bad on unseen data. One way to determine the number of epochs for the training to avoid overfitting is to use the number that results in the lowest error based on the validation data. For our example data, it would be enough to run about 10 epochs to get the lowest error based on the validation dataset. Remember that we can increase the number of hidden layers, which generally means that the network becomes better at predicting the training data. However, that does not necessarily mean that it becomes better to predict the validation data. We can therefore decide the number of epochs and tune the different parameters of the network to find the optimal settings for our network based on the validation dataset. We can also test different loss functions and different activation functions. Since we now have optimized the network based on the validation data, we may encounter overfitting again because we tune the parameters based on this data. One therefore usually also uses a test dataset to estimate the performance of the optimized network based on completely unseen data. The performance based on the test dataset should then reflect how well the network predicts new data. Note that there are a range of different ways you can set up your data to train your network. You can try many different ways to see if you can improve the predictions based on the validation data. Previously, we used only one input value for each input node to predict the price of the stock 1 day forward in time. Another way could be to use, for example, the values from 3 days to predict the 4th day. Then we shift, for example, one step to the right to predict the 5th day and so forth. Since we here give the network more data to train on, it will usually perform better. To increase the performance of the network, we can also use several variables or features as inputs. Suppose that we like to predict the outdoor temperature 1 time step forward in time. Then we can feed the network with variables that we think can contribute to predicting the future temperature. In our previous example, we used the network to predict 1 day at a time over 5 days. All validation data were therefore used to obtain these predicted values. Another way to do this is to train every day, where we update the training with only one new data point each time, and use the network to predict 1 day forward in time. Then we retrain the network by including a new value, and predict. Train, predict, train, predict. Then we can check how well the network predicts when we train it every day. This would correspond to how we can use the network in real life, where we update the network based on today's value of the stock. I will now go through some very basic R codes if you like to set up your first recurrent neural network. Later on, I will also show some Python code and discuss how to create a many-to-one network. I will here use the package RNN, which is very simple to use. You first need to install this package. After you have installed the package, you need to load it. Then we plug in our time series data. Then we normalize this data. By using the following lines of codes, we can make a plot of the normalized data. Then we create a vector with the values for the input nodes, where we remove the last value, and a vector for the target values, where we remove the first value so that it corresponds to 1 day forward in time. Next, we create arrays of the two vectors, where we define that we have one sample, 9 time points, and one variable or feature. If you like the network to be initialized with the same random weights every time you train it, you need to set a seed. By setting the seed to 3, you will be able to reproduce the values of the weights as I have used in this video. Then we train the network with the input values and the target values, with a learning rate of 0.1 and with just one hidden layer. If you run 10,000 epochs, you will be able to reproduce the predicted values shown in this video. We set this argument to true so that the network uses also bias weights. After we have trained the network, which takes about 1 minute, we can use the network to compute the predicted values based on the training data. Finally, we add lines to our previous plot to show the difference between the target values and the predicted values based on the training data. With the following code, you can plot how the sum of the absolute errors changed during the training process. With the following lines, we can extract the values of the weights. Now, let's add the validation data. We then create a vector for the training data and a vector for the corresponding target values. Then we create a vector for the validation data and a vector for the corresponding target values. We then train the network with the same code as before. Next, we predict the training data, which will give us the same values as in our previous code. Finally, we compute the predicted values of the validation data, which show that the model predicts quite bad. We can also compute the sum of the squared errors between the predicted values and the target values of the validation data. The network that we have created is clearly not appropriate to be useful since it cannot predict the validation data. By using the following code that you can find on my homepage, you will get a much better prediction of the validation data. In this code, I stack the data like this so that the network has more data to train on. We use a time series of 5 data points. To predict 1 day forward in time. For this network, I used 10 hidden layers and ran 15,000 epochs, because that resulted in a small sum of squared errors for the validation dataset when I tried a range of different numbers of epochs. The reason why we need to run so many epochs is because we have a very small dataset to train on. For larger dataset, it might be enough to run, for example, just 10 epochs. We will now have a look at the corresponding code in Python using Keras and TensorFlow. You first need to install the following libraries if you have not already done that. Then we import the following libraries and plug in the training data and normalize. Next, we remove the last value in X and the first value in Y and create a 3-dimensional array of the data. To be able to reproduce the results, we set a seed. Try to change this value and note that you will get different results with different seeds, which is due to that the weights are initialized with new random values for every seed. Then we use the function sequential to build a network with 9 input nodes. The reason why we use 9 input nodes is because our time series includes 9 values. This value tells how many variables or features we have in our data. Since we only have one variable, we set this value to 1. This value sets the number of hidden layers or units we like to use. To be consistent with the calculations in this video, we use a sigmoid activation function, but note that you can try other activation functions. Return underscore sequences means, in this case, that the hidden layer should return all its values to the next layer. Then we create one output layer that will receive the 9 values from the hidden layer. Next, we say that we like to use the mean squared errors as the loss function and use an optimizer called RNN. If you print this model, you will see that 5 weights will be estimated. Finally, we train the model by using 10,000 epochs. With this argument, you can tell what will be shown on the screen during the training process. The training process takes about 1 minute on my computer. One can also change the batch size, as we discussed in the video about stochastic gradient descent. If you like to use a certain learning rate, you can change the code like this. Next, we use the model to see how well it can predict the training data. We can then make a plot of the observed values and the predicted values. If you like to see how well the network can predict based on some validation data, we here replace the training data with the validation data. By using the following function, we can print the values of the weights, which are quite similar to the ones we got from the R code. Finally, we can plot how the mean squared error has changed during the training process. Note that we have so far used the following settings to create a many-to-many network. But if we change the code like this, we can generate a many-to-one network, where we use the first 9 values to predict the last value. The nice thing with this approach is that the network is focused on predicting the last value. The model now only gives one output value for the prediction, which is very close to the target value. By using a many-to-one network, we could, for example, set up the network like this, where we plug in the values from, for example, 5 days, to predict 1 day forward in time. Then we move the window 1 step to the right, to predict the next day. This can be seen as we plug in 5 samples, where each sample should predict the corresponding target values. We could then set up the code like this, so that X is now a matrix, and Y is a vector with the 5 last values in the time series. Next, we state that we use 5 samples and 5 time steps. Then we run basically the same code as before, but where we now have only 5 input nodes in our network. Finally, we plot how well the network can predict the last 5 time points in the training data. In summary, there are a lot of different ways you can set up your network, and a lot of different things to tune on. Finding the optimal setting is crucial to create a useful network. By using the following Python code that you can find on my homepage, I was able to get a good prediction based also on the validation data after testing different number of epochs and hidden units. By applying this simple code on a real dataset with a step size of 40, I was able to predict the stock price 1 day forward in time quite well. However, one problem with the basic recurrent neural network we have used in this video is that we might run into the vanishing gradient problem if we use a long time series. To deal with that problem, one can, for example, try to use more advanced recurrent neural networks or use the method of gradient clipping. To run, for example, an LSTM model instead of a simple recurrent neural network, we can change the function simple RNN to LSTM. This was the end of this video about recurrent neural networks. Thanks for watching.